Rotational dampers are defined as elements for which the torque through the element is a monotonic function of the angular velocity. Linear rotational dampers have constitutive equation, and it turns out elemental equation, T equals B omega, where B is the constant of proportionality between the angular velocity difference across the element and the torque through the element. We call B typically the torsional damping coefficient, although sometimes we'll just say the damping coefficient. It's depends on the context sometimes, and we should be more careful with terminology, but we get a little lazy. So linear torsional damping is typically called torsional viscous damping because systems that push viscous fluid through small orifices or those that have lubricated bearings are well approximated by this equation. For this reason, a damper is typically schematically depicted as a drag cup or as a bearing, both of which are shown in figure 1.8. So this is our figure. And a drag cup is an actual device that you can put to couple, put between two shafts to couple them. So if you want to see an example of a shaft coupler, actually in the robotics lab on the bench top where you guys are doing your 316 lab right now, the same device that I told you to look at the flywheel on, the motors are coupled to the flywheels via a coupler. The coupler in that case is a more of a spring-like element. It's a flexible coupler, but there's another way to couple two shafts together, and that's with a drag cup that transmits torque in proportion to the velocity across the shaft. So across the two shafts. So it's a little bit of a different way to transmit torque. One of the main advantages is that they can independently rotate. At low velocities, they're pretty independent of each other. At high velocities, they tend to rotate together. Yeah.
Is that like a torque converter, like a car?
Could be. I think that there are different ways of doing that, but that's one possible way. There are a lot of applications for it. Mainly, it's like a protection with having them be independent of each other. But there are a lot of applications, so yeah. And then, so the other type, so there's the drag cup, which couples two shafts, right? So there's like two different velocities going on. And then there's another type of damper that we're going to talk about, rotational damper we'll talk about, and that's the bearing, okay? So the bearing typically connects the shafts to a housing of some sort, something that's fixed. And the bearing supports, the weight of the shafts. It gives a hopefully pretty smooth support, so it doesn't add a lot of friction. It would be very bad bearing if it was adding dry friction. Typically, we can model it pretty well by being a sort of viscous damping. And the sort of the one thing to keep in mind here is that the shaft is considered in this to be a continuous angular velocity. So the shaft is at one velocity, and then the housing is 0 velocity. It's like a very offended person up here about that sneeze, and I'm not sure why.
I thought it was Parker. He sneezed like 30 times. They're one story.
Unacceptable. Yeah. No. Sneezers, man. Yeah, so damping, right? The shaft can be damped sort of between two shafts, sort of coupling them, or it can be connected to the ground, to the support through a bearing. So, linear damping is a reasonable approximation of lubricated sliding, but is a rather poor approximation for dry friction or Coulomb friction, forces for which are not very velocity dependent. And this is exactly what we said for linear damping as well. Dry friction in the translational domain is very poorly approximated by damping in this way. And it's the same with rotational damping. Rotational dampers dissipate energy from the system, typically to heat, making them energy dissipative elements. So those are the only ones we have so far, elements that dissipate energy from the system. Okay, so we've got to get energy into the system, and we do that through torque and angular velocity sources. So an ideal torque source is an element that provides arbitrary energy to a system via an independent torque. So the torque is set independently of the system, and the corresponding angular velocity across the element depends on the system. Okay? So we drew the analogy between torque and current, right? So this is kind of like a current source. An ideal angular velocity source is an element that provides arbitrary energy to a system via an independent of the system angular velocity. And the corresponding torque through the element depends on the system. So this is kind of like a velocity or a voltage source, right? That provides a voltage, and whatever current is required, it provides. That's what we've got here. Yeah, so this is rounding out the mechanical rotational elements, lumped parameter elements that we're going to consider. And they're pretty, these are definitely the highlights of mechanical elements. There are a lot of details, obviously. So you can get into a lot of detail on how to do the rotational mechanical system modeling. So you can try to decide a priori, like looking at the analysis of the system, what is the, based on geometry and material properties, what are the moments of inertia, what are the damping coefficients and spring constants, etc. And you can also do testing for that. So just like with translational mechanical systems, we can do testing, and we can also try to come up with a theoretical prediction for what these properties could be. As with translational mechanical systems, spring constants and moments of inertia are relatively easy to predict without having to do any testing, but the damping is almost always the hardest thing. So we'll often end up trying to measure that, or we'll use some detailed model or detailed simulation to try to figure out what that would be. Or if it's a relatively simple case, if there's a sort of standard type of device, then we can use design equations that aren't too bad. So based on just a simple calculation. So depending on the situation, we'll use different methods to find the lumped parameter model parameters. Yeah, lumped parameters. Okay. Any questions on rotational elements? All right, we'll finish that up then.